Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. Please allow me to introduce myself. I'm Philip Emeagwali. I was a research supercomputer scientist of the 1970s and 80s. In those 2 decades, I conducted undisturbed, unprecedented, and bleeding-edge supercomputer research and speed measurements. And I conducted both at the farthest frontiers of the fastest computations ever recorded. I conducted experiments on how and why the speed of the modern supercomputer increases when supercomputing across a new internet that I visualized and invented as a new ensemble or as a new global network of 65,536 tightly coupled commodity off-the-shelf processors that were married together by 1,048,576 email wires. I invented that new internet as a new supercomputer and as a new computer. That new supercomputer is best used to solve the toughest problems arising in extreme scale algebraic computations, modern calculus, and computational physics. In supercomputing, the light at the end of the tunnel becomes brighter with each supercomputer speed increase that is experimentally confirmed. The reason a mathematician from my country of birth, Nigeria, developed cold feet over parallel processing the most extreme scaled problems arising in algebra is that mathematicians' lack of the understanding of how and why the most extreme scaled problems arising in algebra arises from the partial differential equation of modern calculus. The reason Nigeria did not fund my research in the parallel processing supercomputer, and the reason the research computational mathematician in Nigeria of the 1970s and 80s shied away from physics-based simulations that were extremely computation-intensive modern calculus, and why that algebraic knowledge must be used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas that is buried 1 mile deep inside the oil fields of the Niger Delta region of Nigeria. I was asked to explain how my contribution to algebra can be studied in your high school algebra class. In high school algebra, you learned how to use pencil and paper to exactly solve for 3 unknowns from a coupled system of three simultaneous equations. Your high school algebra textbook did not attempt to teach you how to exactly solve for four unknowns from a coupled system of four simultaneous equations. The reason your high school algebra teacher did not cover a system of four simultaneous equations was that the arithmetical operations count that must be executed to know the four unknowns was more than you can handle. For that reason, extreme scale problems in algebra, such as solving for a million, billion, trillion unknowns and solving for them from a coupled system of a million, billion, trillion simultaneous equations, must be solved not on your computer, but solved across a new internet, that is a new supercomputer and a new computer. On the 4th of July 1989, I mathematically and experimentally discovered how to exactly solve for 24 million unknowns from a coupled system of 24 million simultaneous equations that was the largest algebraic problems arising from any physics-based simulations within a multidisciplinary environment. My world record solution of the toughest problem arising in algebra was the cover story of the top mathematics publication, namely the May 1990 issue of the Siam News. I was the cover story of top mathematics publications, not because I was good looking. I was the cover story because my mathematical discovery was a giant leap forward in the development of the modern algebra. I discovered how to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. Back in 1989, the 24 million equations of algebra that I discovered how to solve and how to solve them simultaneously and across a new global network of 65,536 tightly coupled commodity off-the-shelf processors that shared nothing between each other, that is a new internet by definition, was impossible to solve on the most powerful vector processing supercomputer. A 12-year-old writing a school report titled Famous Mathematicians and Their Contributions to Mathematics asked me, "What is your contribution to algebra?" I answered that my contribution to algebra is this: I mathematically and experimentally discovered how to parallel process across a new internet that is outlined and defined by 65,536 processors that uniformly encircled a globe. On the 4th of July 1989, I experimentally discovered how to parallel process and how to push the frontier of knowledge of modern algebra and how to push that frontier by a breathtaking factor of 65,536. Shortly after my discovery that occurred on the 4th of July 1989, it made the news headlines that I, Philip Emeagwali, had experimentally discovered how to communicate and compute, and how to execute both collectively and across a new internet that I defined as a new global network of 65,536 processors, and that I discovered how to solve the toughest problems arising in extreme scale algebra, and I discovered how to solve those problems 65,536 times faster than one processor solving the same problem alone. That 65,536-fold increase in supercomputer speed increases the user's productivity while reducing the user's time to market. In the old way of solving the most computation-intensive problems in large-scale algebra, and before my experimental discovery that occurred on the 4th of July 1989, the most extreme-scaled algebraic computations were solved across a customized and expensive vector processor that processed only one thing, or string of numbers called vectors, at a time. That vector processing supercomputer was the fastest supercomputer in the decades of the 1970s and 80s. But in the new way, or the new parallel processing supercomputer that I mathematically and experimentally discovered on the 4th of July 1989, and discovered in Los Alamos, New Mexico, United States, I discovered how to solve in parallel the most extreme scale problem arising in algebra. And I discovered that technology by parallel processing that algebraic problem across 65,536 commodity off-the-shelf processors that I visualized as a new internet, that is a new global network of 2 raised to power 16 commodity processors. Parallel processing was described as a grand challenge for a good reason. As a lone wolf, massively parallel processing supercomputer scientist of the 1970s and 80s that was not a member of a 400-person supercomputing team, there were times I felt like I was like a solo air traffic controller on planet Earth that was tasked to direct 65,000 identical planes in the air, and tasked to simultaneously, safely, and properly land those 65,000 identical planes and land them on 65,000 identical runways that were equal distances afar and apart from each other and on the surface of a globe the size of the Earth. That was the reason the June 14, 1976 issue of the Computer World magazine scorned parallel processing and mocked the then unproven technology as a huge waste of everybody's time. The toughest problems in computational physics are linked by a common thread, namely extreme scale algebra that in turn must be parallel processed across millions upon millions of commodity off-the-shelf processors. In the old paradigm of algebraic computation, the most computation-intensive problems arising in algebra were sequentially solved by executing only one floating-point arithmetical computations at a time. In the old paradigm of algebraic computation, it was mathematically impossible to email subsets of the tridiagonal system of equations of algebra and email them across my ensemble of 65,536 commodity off-the-shelf processors. In my new paradigm of explicit finite difference algebraic approximations, I made the impossible possible. And I did so by reimagining the toughest problem in calculus, namely the excruciatingly detailed simulations within a multidisciplinary environment of three-phase flows of crude oil, injected water, and natural gas that were flowing across a production petroleum reservoir, and re-envisioning my governing partial differential equations as hyperbolic, and doing so when the calculus textbooks describe them as parabolic. My inventions of those 9 partial differential equations, called Philip Emeagwali's equations of a new calculus, and my inventions of their companion and approximating 9 partial difference equations of a new algebra is my contributions to mathematical knowledge. My contributions to mathematics made the news headlines across major US newspapers, and it was the cover story of the top mathematics publications, such as the May 1990 issue of the Siam News that was published by the Society for Industrial and Applied Mathematics. It was not my looks, wealth, or family connections that put me on the cover of top publications in the field of mathematics. It was the 9 Philip Emeagwali's equations of modern calculus that I invented that put me on the cover of the Siam News and on 2 postage stamps. My contributions to computational mathematics changed how the petroleum industry uses the modern supercomputer to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. Before my invention, or before 1989, petroleum reservoir simulations were executed on only one processor that was not a member of an ensemble of processors. After 1989 and today, all extreme scale petroleum reservoir simulations and computational physics codes are executed across an ensemble of up to 10,649,600 commodity off-the-shelf processors. The first oil field in West Africa was discovered in 1956 and at Oloibiri in the eastern region of colonial Nigeria. Because the oil discovered in 1956 at Oloibiri oil field of Nigeria was buried 1 mile deep, we cannot see its 1 mile deep movement towards the oil and natural gas production wells that were also 1 mile deep. We cannot see the 1 mile deep subterranean motions of oil and natural gas with our biological eyes. However, we can use our mathematical eyes to abstract the three-phase subterranean motions of crude oil, injected water, and natural gas, and to hindcast how the most crude oil and natural gas will flow towards production wells. Because the crude oil and natural gas discovered offshore of the Nigerian coastal waters and deep under the ocean floor, or discovered onshore in Oloibiri, Nigeria, was 1 mile deep, we cannot see how that crude oil and natural gas flows from water injection wells to oil and natural gas production wells. We cannot directly see the flowing oil and natural gas and see the oil and natural gas directly as we directly see water flowing across the River Niger of West Africa. But our geological data from the Niger Delta region of Nigeria that includes the initial and boundary conditions of the governing initial boundary value problem, and our knowledge of the laws of physics, and my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July 1989 enables us to see across my new internet, that is a new global network of 65,536 tightly coupled processors that were commonly available in the market. That is the massively parallel processing computational physicist can intellectually see within a massively parallel processing supercomputer and see oil and natural gas that the vector processing computational physicist cannot intellectually see, and that the ordinary person cannot even see with his biological eyes. The massively parallel processing computational physicist that mathematically sees deep inside the Niger Delta oil fields of southeastern Nigeria enables us to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. In 1989, it made the news headlines that I experimentally discovered how we can use our parallel processing supercomputer eyes, or use a new internet that is a new global network of tightly coupled commodity processors as our instrument of physics, as well as use the technology as our tool for oil and natural gas exploration. Conversely, if the petroleum industry didn't accept my invention and didn't harness my ensemble of 65,536 or more commodity off-the-shelf processors and didn't use them in their petroleum reservoir simulations, then less oil and natural gas will be discovered and recovered. My experimental discovery of the massively parallel processing supercomputer changed the way the petroleum industry discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. My experimental discovery of how and why parallel processing makes the modern supercomputer fastest changed the way we think about how to build the fastest computer. It made the news headlines in 1989 when I experimentally discovered that we could execute extreme-scale computational physics codes and execute them across an ensemble of 65,536 tightly coupled commodity off-the-shelf processors that shared nothing between each other, that were identical to each other, and that were equal distances afar and apart, and that I visualized as a new internet that encircled a globe in 16-dimensional hyperspace. My contributions to extreme-scale computational mathematics are mathematical discoveries in both algebra and calculus that are, mathematically speaking, both abstract and obscure. However, you benefit from the new algebra and the new calculus that I contributed to mathematical knowledge. The petroleum industry used my contributions to extreme-scale mathematical computations and used the new mathematical knowledge within the supercomputers it uses to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. My discovery is the reason 1 in 10 supercomputers are purchased by the petroleum industry. My contributions to computational mathematics was the reason I was invited to deliver a lecture to research mathematicians attending the International Congress of Industrial and Applied Mathematics called ICM 91. That Congress was the largest gathering of mathematicians ever. To quote myself from that ICM 91 lecture that I gave on July 8, 1991, to the International Congress of Industrial and Applied Mathematics, I said, quote, in extreme-scale petroleum reservoir simulations, the governing system of partial differential equations of the modern calculus are often anisotropic or have coefficients with strong directional dependencies. That is, my differential operators are position-dependent, non-axis aligned, and have privileged spatial directions. I invented new partial difference equations that I defined across 2 and 3-dimensional grids. I used my new finite difference algorithms to discretize my new system of 9 coupled nonlinear, time-dependent, and state-of-the-art partial differential equations of the modern calculus that I also invented in the early 1980s, unquote. I continued my lecture of July 8, 1991 at the International Congress of Industrial and Applied Mathematics in Washington, D.C. Quote, the first tridiagonal algorithm that I investigated on a sequential processing supercomputer back in 1974 in Corvallis, Oregon, that was the first supercomputer to be rated at 1 million instructions per second, was a three-step adaptation of Gaussian elimination. That algorithm converged to my solution where my tridiagonal system is diagonally dominant. That is, the norm of the diagonal entries must be greater than the sum of the norms of the subdiagonal and superdiagonal entries, unquote. I continued my lecture of July 8, 1991 at the International Congress of Industrial and Applied Mathematics in Washington, D.C. Quote, in the first step for solving my tridiagonal system of equations of algebra, I factorized the coefficient matrix into lower and upper triangular matrices that were each bidiagonal. If the size of my linear system of equations of algebra was n by n, or a million billion trillion by a million billion trillion, I performed a priori 2 times a million billion trillion multiplications plus a million billion trillion additions. In the second step, for solving my tridiagonal system of equations of algebra, I performed a forward substitution on the lower triangular bidiagonal matrix. My a priori computational workload for this second step was a million billion trillion multiplications plus a million billion trillion additions. In the third and final step for solving my tridiagonal system of equations of algebra, I performed a backward substitution on the upper triangular bidiagonal matrix. My a priori computational workload was 2 times a million billion trillion multiplications plus n additions. And my total a priori computational workload in floating point arithmetical operation counts for all 3 steps was 5 times a million billion trillion multiplications plus 3 times a million billion trillion additions, unquote. I mathematically discovered that it's both logically and physically impossible to massively parallel process the solution of a tridiagonal system of equations of algebra, but it is possible to parallel process the solution of a diagonal system of equations of algebra. As an extreme scale computational mathematician that was supercomputing petroleum reservoir simulation codes and supercomputing them across my ensemble of tightly coupled commodity processors, my end was not to merely solve a tridiagonal system of equations of algebra. We solve systems of equations of algebra to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas that are buried 1 mile deep inside oil fields, such as the Niger Delta oil fields of southeastern Nigeria. I stepped backward to the laws of physics to reformulate the partial differential equations of modern calculus to obtain an algebraic system that's diagonal. At the International Congress of Industrial and Applied Mathematics, and as a research computational mathematician in quest for never before seen mathematical equations, I explained that I invented 9 never before seen partial differential equations of modern calculus. That is, I invented partial differential equations that fit the second law of motion of physics rather than invent a law of motion of physics that fit the partial differential equations on the mathematician's blackboard and in the calculus textbook. Back in June 1974, at the Computer Center at 1800 Southwest Campus Way, Corvallis, Oregon, United States, this Gaussian elimination algorithm for solving a system of tridiagonal equations of algebra was efficient when the supercomputer scientist must do only one thing at a time. The tridiagonal algorithm is efficient for sequentially processing supercomputers because, in part, I did not have to store the off-diagonal zeros. The tridiagonal algorithm was the workhorse of algebraic computations on a sequential processing supercomputer, and remains so. Due to its success, computational mathematicians misconstrued the tridiagonal algorithm as the end instead of as one of the means to the end. The end for an extreme scale computational physicist, that is parallel processing across millions upon millions of tightly coupled commodity processors, is to attain a surer and deeper understanding of how the universe works and how to harness that new knowledge of the partial differential equations of planet Earth to make planet Earth a better place for human beings and for all beings. The end for an extreme scale computational geophysicist is to use high petroleum reservoir simulator as a digital divining rod for discovering and recovering otherwise undiscoverable and unrecoverable crude oil and natural gas, such as recovering some of the 70% of the crude oil and natural gas discovered in Oloibiri oil field in Bayelsa State, Nigeria in 1958 that was abandoned 20 years later in 1978. Back in the supercomputers of 1974, with very limited storage, I stored the non-zero entries of my tridiagonal systems as three vectors. The tridiagonal algorithm is inherently sequential, and for that reason is a curse to the programmer of the modern supercomputer. The tridiagonal algorithm is a curse because the massively parallel processing supercomputer scientist wants to massively parallel process across 65,536 tightly coupled processors that shared nothing between each other, or to massively parallel process across as many computers, or to solve 65,536 algebraic problems at once. The tridiagonal algorithm of the 1950s sequential processing supercomputers that was widely hailed as a blessing for alternating direction implicit methods used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas became a curse in the early 1980s when I tried to parallelize the mathematically impossible to parallelize, namely to massively parallel process an inherently sequential algorithm by solving many algebraic problems at once or in parallel. Abstract mathematics is an art on the blackboard and an experimental science on the motherboard. I am an experimental mathematician of the 1970s and 80s who used his system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus called Philip Emeagwali's equations, and used that system to experimentally discover the massively parallel processing supercomputer. Extreme-scale computational mathematics becomes magic when it is executed across 2 to the power 16 tightly coupled commodity off-the-shelf processors that share nothing between each other, that are identical to each other, and that are equal distances afar and apart from each other. I experimentally discovered how to solve the toughest problems arising in modern algebra, and how to solve those problems across my ensemble of 65,536 processors, and how to solve them when my ensemble emulates one seamless, cohesive, massively parallel processing supercomputer that was the precursor to the modern supercomputer. That new supercomputer is not a computer per se. That new supercomputer is a new internet de facto. I experimentally discovered the precursor to the modern supercomputer, and I discovered it at 8:15 in the morning at Los Alamos, New Mexico, United States time of Tuesday, the 4th of July, 1989. That experimental discovery put me in the news headlines of major US newspapers as the African supercomputer wizard that won top US prize and won it for his contributions to the development of the massively parallel processing supercomputer. Behind each of those 65,536 tightly coupled processors that outlined a new internet was a lone wolf research supercomputer scientist that was not a member of a 400-person research team that coded and verified each line of his massively parallel processing instructions and invented each partial difference equation of his extreme scale algebra that had to be solved across those 65,536 processors, with each processor operating its own operating system and with each processor having its own dedicated memory that shared nothing between each other. That research supercomputer scientist invented each partial differential equation of modern calculus from which those algebraic equations arose. I, Philip Emeagwali, was that research massively parallel processing supercomputer scientist that ensured that his 2 raised to power 16 or 65,536 message passed supercomputer codes were one-to-one mapped to 65,536 16-bit identified processors, and ensured that the codes and processors came together as the fastest and never before seen supercomputer that made the news headlines across major US newspapers, and that was reported in the June 20, 1990 issue of the Wall Street Journal.
insightful and brilliant lecture.